Okay, so in today's session, we're gonna go over what Blobstream is, what Celestiums are, and we're gonna go deeply into explaining how you can create inclusion proofs with Blobstream and how rollups can use what Blobstream is. So Blobstream is traditionally what you used to have is that you had your execution layer. And you had your settlement layer, which can be, for example, an EVM chain, for example, Ethereum. So what would a rollup do is that it would send its data to the settlement layer and also send all the Merkle proofs to it. So, for example, if you have here the settlement contract, and this is the call data. So what's going to happen here in this execution layer, which is basically a rollup, is that you would be sending the Merkle root to the contract and also sending the rollup data to the call data and save them as call data. However, with Celestia, what you can do is that you can change this. So let's assume you have Celestia here. What we're going to do now, if we want to create a Celestium, we're going to be sending this rollup data. Here, let's call it data. And here, Merkle roots. We're going to be sending this data to Celestia. So now what happens is that we no longer need to rely on the call data in the settlement layer, and the contract can be sure that the data exists on Celestia via the bridge called Blobstream. So basically what we are doing is that we are reducing the cost to operate your rollup, your execution layer, via sending the data to Celestia instead of committing to it in the call data. And here where we have our Blobstream here, where Blobstream is committing to Celestia data, and the settlement layer is going to use Blobstream to read and verify the data was posted. So this is basically it. This is basically what a Celestium is. You have your data. Instead of sending it to your settlement layer, you send it to Celestia. And you verify that using Blobstream. So the difference between Blobstream and data availability committees or centralized bridges is that you could be using a data availability committee. It's easier to use and all. But the thing that data availability committees don't give you is that it doesn't give you the ability to slash. So you don't have a way to prove that your data was actually posted to the DAC or was not posted to the DAC. And also, in case of something bad happens, you wouldn't be able to slash them. So this is what Blobstream it gives you two important features. The first thing is that it gives you an external consensus that you can use to slash in case some validator basically misbehaves. And also the second thing that it gives you is that you'll be able to verify the data yourself. If you would be able to verify the data when using Blobstream or even before you can use it. And that is using data availability sampling. So basically what you'd be doing is that you can verify that all the data exists without having to download most of it. So you'd only be downloading less than 1% of the data and be 100%, 99% sure that the data exists. So basically what Blobstream gives you is that it inherits all of the security guarantees of Celestia and allows you to slash in case you didn't have access to the data. So now we can go to check how Blobstream works on the inside. Let's assume that we have our Celestia here, a Celestia block. So this is a Celestia square. That has data that has been posted to Celestia. So we can assume, for example, that we have our rollup data here. It's been committed, for example, to this place here. Celestia provides you here, when you create the square, you have like row roots here, you have rows. This is, for example, row 0, row 1. And also we have columns like col 1, col 0, col 1. So the way that we create our data structure is that we put like the blob data in a place in the Celestia square, and then we commit to it. We commit to it using, first we start off by using an NMT, a namespace Merkle tree. And the way that we create that is that we take, for example, this row here. Like, for example, if we take this this row here, and we can have it, for example, here, where we have our roll-up data here. So this is row 1. So what we're going to do is that we're going to create a namespace Merkle tree out of it to create the row root. The way we do that is, like, you can find like the namespace specification in the Celestia documentation. And basically what we have here, what we're going to end up having is the row root 1. Then we're going to do like the same for row 0 and row 2 and row 3, and also the same thing for column 0, column 1, 2, and 3. So once we create those, we can assume that we have them here, for example. And also the columns. And then when we take all of these, then we're gonna create a Merkle tree, a binary Merkle tree out of them. And the way we're gonna do it is like how you basically create a Merkle tree, and then we're gonna create all the commitment for it to be able to have here what we call in Celestia the data root. The data root basically commits to all of the data that has been posted to the Celestia block, and for each block you have a specific data root. So now in this case here, if you, for example, if we want to take, if we take, for example, this blob, this share here, which can contain, for example, your, I don't know, some transaction and all, and you want to prove that it exists on Celestia, you could have the data root, and then you're gonna need, first you're gonna need this, and then you're gonna be able to have a Merkle proof from this share to the row root, and then you're gonna need this and this too, and probably something here to be able to get to the data root. So once you have that Merkle proof, you're gonna be able to prove that this transaction is part of the data root. So now when we have our data root, like we can assume like we have multiple blocks here, so we're gonna have multiple data roots. So let's assume we have here data root, for example 0. So what we're gonna do is that we're gonna also add the height to it, so it's gonna be height 0 here, and then we're gonna have, for example, data root 1 and height 1, data root and height n. So let's assume like all of these represent some Celestia blocks. Like for example, this one is this one, and the others come from like the whole chain. So what we're gonna do is that we're gonna take these data root tuples. We call them data root tuples because like it's a tuple containing the data root and the height, and then we create a binary Merkle tree out of them. Something like this. And then what we end up with is something called the data root tuple root. So basically what this is, like a data root tuple, which is this, and this is like the root of all of them. So if we take, for example, this data root tuple, we can create an inclusion proof for it to this data root tuple root, and it's gonna be basically this. You're gonna need these nodes, and then you would be able to like have a proof of this data root tuple to the data root tuple root. So what we have here is that once we create all of these, then we send this to Blobstream, to the Blobstream contract. For example, let's assume we have Blobstream contract here. Can push maybe a bit this, like this. So what we do is that we take these data root tuple roots and then we commit to them in the Blobstream contract. So what happens is that if you have, for example, your transaction, if you assume this is the rollup data and this is all the rollup data, and we have, for example, a single transaction that we are interested in proving that it was posted to Celestia, what we do is that we take, for example, this is the transaction, we create the first Merkle, namespace Merkle proof from this transaction, from this share to the row root one, and then we create a binary Merkle tree, Merkle proof from this row root one to the data root via using these nodes, and then we take this, like this is the proof to the data root, and then we add to it the height, and then we create a Merkle proof of a binary Merkle proof of this data root and height to the data root tuple root, and then once we have all of this, and this one is committed to by Blobstream, we are able to prove that this share was part of the Celestia block in Blobstream. So this is basically how an inside inclusion proof would look like in Blobstream. And now we can go and see like how like Blobstream commits to all of this data. Okay, so we create a new page. So now at this level here, we were able to understand like how an inclusion proof would work from a single share in Celestia to the data root tuple root in Blobstream. And now we can see how we can, like, how would a rollup use Blobstream to verify that its data was posted to Celestia. Okay, so we can have here, for example, our Blobstream. And we can assume, like, for example, we have our rollup contract here. So the rollup contract is gonna commit when, like, after like creating its data, its block, and then it's gonna, after it sends it to Celestia, it's gonna commit to like some information about Celestia that's gonna be used to create like an inclusion proof of Blobstream. And like we can define here something called a span that we can use to create this proof, and which can contain like a height, a data starting index, and a data length. And this is like only if we want to, like if we assume that this rollup contract is sending its data only to a single Celestia block. But if it is sending its data to multiple Celestia blocks, then you can generalize this to include multiple blocks. So now that we have these, then we would be able, like for example, if we want to prove that the data is unavailable on Celestia, like if we want to prove that this, like if we want to have a fraud proof, for example, to prove that this data was not posted or doesn't exist, that boils down to proving that this data is out of the square, Celestia square. Like for example, if we assume that we have here a Celestia square, and this is the erasure encoded data. So proving that the rollup data does not exist goes down to proving, for example, that this provided range here is, for example, out of the square, is something here. It's out of bounds of the square. And the way that you can do that is, if you go back to the proofs that we just created, you can, for example, you can prove that, you can create, for example, a Merkle proof of, for example, this row root to the data root tuple root. And what this would give you is that it would give you, inside the proof, it would be sure that this row root was in fact, indeed, like part of that Celestia block at that certain height. But like what it would also give you is that the numbers of rows and columns, which you can use to calculate like the size of the square. And once you calculate the size of the square, you would be able to compare it to the span here and be like, okay, so we have, like, for example, a square size of 16, and then we have like a start index of 1 and a data length of, I don't know, 60. So that means that this data span is out of bounds from this Celestia block, and you can be sure that, okay, so this data was not posted to Celestia. And the second thing that you can prove using a rollup contract is that if you have like some invalid state transition that you want to prove occurred, what you can do is that you can go back here to these, is that you can go back here, and for example, if you want to prove that in here, like in here some invalid, I don't know, here some invalid state transition happened, is that you could create your Merkle inclusion proofs from this share to the row root, and then from the row root to the data root, and from the data root tuple to the data root tuple root, and then you would be sure that this data is exactly what was described in the in this span, for example, and then you would be sure that this data like is the rollup data, and then you can parse it, for example, inside the rollup contract, and then execute the logic to prove the transaction is invalid. So this is typically how a rollup would use Blobstream. Then we can move to explaining how Blobstream X, an implementation of Blobstream that uses ZK proofs, works. So here, so basically what Blobstream does is that it takes the Celestia block headers and it creates a ZK proof from them, and then in the Blobstream X contract, it verifies that proof, proving the like the Tendermint Lite client verification, and then you could be sure that like if the proof is valid, then the Celestia blocks were valid, and also what's committed to Blobstream is also valid. So the way that works is that, let's assume we have here a bunch of Celestia blocks. So what would Blobstream X do? What would a prover do is that it's going to take these headers and then create a Plonky 2x proof of them. The good thing about Plonky 2x proofs is that they are super fast to be generated, and also they provide good recursion features. But the problem with them is that you can't verify them easily on EVM chains. So what we do is that we take this proof and we wrap it inside a Plonky ZG proof, which is easier to be verified on EVM chains. So once we have this Plonky KZG proof, then we send it to, like we can assume here we have, for example, Ethereum. And then we send it to Blobstream contract to be verified, basically via passing by some smart contracts like the gateway and the function verifier, function ID verifier. So once we send this proof here, Blobstream X is like Blobstream X verifies this proof here that is like a Tendermint Lite client verification, and then once this verification is done, a data root tuple root like we described earlier gets saved inside the Blobstream X contract, and then you can use it for rollups and all. I guess this is it. If you have any questions or anything. Okay, so.
Why would you need to prove things that are out of bound? Did you cover that?
Well, yeah, if, for example, the rollup contract, like attests that we have some, like that the rollup contains some data, and then it commits to a span that doesn't exist. So what the rollup would be having is that it would be losing its data. So if you have like your chain and it doesn't have access to some part of its data, then that's bad. You would need to be able to prove that in the rollup so that you can slash or do something. Like traditionally what you would do is that you had all the data being committed in call data, so you could actually verify that the data exists or not. But since now it is part of Celestia, you would need to go via creating like an inclusion proof that gives us the square size and then verify that this data is actually part of the square size using Blobstream to be able to be sure that the data exists and like the data is not missing.
The original question was just trying to get at why we would ever want to prove that some data was outside of the square. And then I think the second topic that we could talk about maybe a little bit more was like Optimistic and ZK, how they actually use Blobstream.
Okay, we can look at how we can do this. So for example, if we have Blobstream here, and we have here our rollup, and we have here Celestia. So what's going to be here is the data is going to be sent to Celestia, and then here we're going to commit to that data, and here we can verify. So for an optimistic rollup, you can get away with, like, whenever you send your data to Celestia, you can just create the span that we just talked about, and then once you have your span, then you are given like a data pointer to people who would want to verify that the data is on Celestia, and that's it. But like once someone doubts that, they can like start verifying themselves, and if like they find like that some data does not exist, then they can create a fraud proof and verify it using Blobstream, like we said, using the inclusion proofs and everything to be able to know if the data actually exists or not, and if that data contains some like invalid state transition. For ZK rollups, they have like wouldn't be worrying about like the integrity of the transactions inside, but we would be worrying about if the data actually exists or not. So what ZK rollups would do is that they would create a ZK proof of their rollup state, and then once that is verified, they would also need to verify that the data was posted to Celestia, and they would verify it using Blobstream. So that boils down basically to verifying that the height exists, the data commitment, the data root is correct, and also proving that like the span is pointing to valid shares and all. So this is how optimistic rollups and ZK rollups would use Blobstream and Celestia.
And from an implementation detail standpoint, can you explain where the information in the data root triple root is coming from? Like, for example, like if
you mean this one?
Yeah, like is the rollup running, or like how is like the Blobstream contract, for example, like tracking like the data roots and the heights to then be able to like know how to prove like which block it's included in? Okay,
so we can go over like this is how this like for example we assume like we have a certain, for example we have a transaction here, we have some block data here that is being sent to Celestia. So once this data here is sent to Celestia, then that data is going to be put inside a square, inside the Celestia square, like this one. So we can assume, like, for example, this is the rollup data that was just sent. All the transactions and all are in this place here. So once you have this, then you start creating like commitments over this data. So basically what the data root tuple root attests to is that it attests, like it is a 32 bytes string that you can use that commits to this data root and height, and also other data roots and heights. And this one, for example, contains all of these row roots, which in turn commit to the data. So basically what in Blobstream is just this commitment. And if you want to prove something exists or not, then you create a proof from this like Merkle inclusion proof, like using, for example, these nodes here to create a proof to the these nodes here to create proof to the row root, and then these nodes here to create the proof to the data root, and then these nodes to create the proof to the data root tuple root. And that way, like if you manage to create this kind of structure of proof, then you can be sure that this data was committed to by the data root tuple root. So what Blobstream keeps track of is a bunch of data root tuple roots, and it's up to you to create like all the proofs or the proof that something doesn't exist in it.
Okay, so like how Blobstream is like, or what data root tuple roots Blobstream is tracking is basically just based on whenever there is a transaction that it's concerned with. Like I'm
Well-
trying to think about like thinking like at a high level, like, you know, data routes are obviously like, you know, created for every block, right? It's in every header.
Yes.
And so I'm trying to understand like what is like the trigger for creating a new data route, Drupal route that like Blobstream X would be tracking. Is it only when it is submitting a transaction that it's concerned with, or is it on
Well-
like header receipt or you know?
Well, actually, like we have here, like the traditional Blobstream implementation, we were committing for every 400 blocks. So we'd be committing like if you have once Blobstream, like it finds like that there is like 400 blocks, then it would create like all of this for it, and then it would
okay.
commit to it. But in the Blobstream X implementation, we are doing like 60 minutes delays, so that every 60 minutes you create a proof of everything that has been since.
Okay, all right. So it's
since the last
that
proof,
kind
yeah.
of like preset
Yes.
interval. Got
So
it.
like
Okay. Makes
Blobstream
sense.
X is committing like since it's going to be committing to since its deployment to the tip of the chain. Like all of that, you could create proofs for it.
Cool. Thanks.
Sure.
Is there any penalty for a validator to do a wrong relaying of the data route tuple route when it is posting to Blobstream? Like, would it suffer any penalty for relaying wrong information about
Well,
data routes?
in the old implementation, which we were actually like depending on validators to like to create the signatures for the data route tuple routes and then sending them, we would have like to do a manual process of like slashing them. But we didn't have implemented. But now with Blobstream X, you can't actually like if you assume that you created like a correct Plonky2X proof, Plonky2X circuit is then you have your block headers and then you create a proof from them, and then this proof here gets verified here. So if you have an invalid like header or invalid signature, then it's not gonna pass here. So it's not gonna be there. And if you have, for example, some validator creates, for example, another block that contains, for example, 2 signatures and all, we should be able to, for example, take that signature and submit it in Celestia and be able to slash them because like they equivocate. Yeah.
Yeah, I guess the second part I
okay.
think that answers the question. But how does it still relay it from Ethereum to Celestia? Because the bridge is one way, I guess.
Well, it's not like relayed from Ethereum to Celestia. Like you're gonna have to have that logic in the prover, for example, that if it finds like a header with 2 signatures and all, then it would send it.
So it would be part of Celestia core?
Well, it's gonna be part of it's gonna be evidence, but like I would need confirmation from Evan and Ismail on that, maybe.